In this video, we're going to talk about subspaces, but not subspaces of just Euclidean spaces, but subspaces of general vector spaces. So our definition is going to be almost exactly the same. If you have a subspace of a general vector space, that means using the appropriate vector addition and scalar multiplication for that subspace, then you cannot add your way out of that set W, and you can't scale your way out of it. So you're closed under vector addition and closed under scalar multiplication. Now, we know that if you have a vector space, the first two axioms of those 10 axioms ensures that it's going to be a subspace. But what about the opposite? Is a subspace also a vector space? What will we need to do? We'd have to check the remaining axioms. Obviously, if it's a subspace, the first two axioms are satisfied. So what about the other 8? Well, we know that if you take any vectors, u, v, w, in the parent space and any real scalars, those 10 axioms are going to be true. So what if I take 3 vectors from W, so our subspace, and 2 scalars, which are real numbers? Will the other axioms be true? Well, I don't want to go through all of these, but let's just say, okay, the first 2 we know we're going to get true because that's the definition of a subspace. But the other ones are either inherited, because since you have all the vectors in W belonging to V, then the vector addition properties have to hold because those are vectors which are also in V. The distributive properties have to hold, again, because all of the vectors in W are vectors in V. And the other scalar multiplication properties hold for the same reason. And then what about the existence of the zero vector? Well, the zero vector has got to be in W. And why is that? Because if you have any vector in W and you multiply it times the scalar 0, you're going to get the zero vector. So that's got to be in W. So you can't scale your way out of W. And then, again, if I scale a vector in W by -1, I get its additive opposite. So, if W is a subspace of a vector space, then W itself is going to be a vector space. And I don't know why I changed the order here. That's just a typo. It should be O plus and then O dot. So what does this say? It says that W is a subspace of V if and only if itself is a vector space, if it satisfies all 10 of those axioms. Just like in Euclidean spaces, the appropriate zero vector, whatever the zero vector means, has to belong to the subspace W. And if it's not in there, then it can't be a subspace. But we do know that even if you have the zero vector in a set, that doesn't automatically make it into a subspace. And here's a simple example from Euclidean space R2, that the set where of ordered pairs where y equals x squared, that contains 0, 0, but that's not a subspace because, well, you can scale your way out of it, right? 1, 1 belongs to W, but 2, 2 does not belong to W. No, it would be 2, 4. All right, what are some subspaces? Well, remember, f of R means that the functions which are defined on the entire real line, where f of 3 equals 0. This is a subspace. Well, quick check. Does it contain the zero vector? Well, what's the zero vector for functions? Is this zero function, z of x equals 0 for all values of x. Well, if it equals 0 for all values of x, then z of 3 equals 0. So it belongs to our subspace W. We need to verify the closure properties now. Can we add our way out of it? If I have two functions where f of 3 equals 0 and g of 3 equals 0, if I add them together, will this new function, which is the sum, evaluated at 3, will that also equal 0? Well, we know how to evaluate the sum of functions at a single point. You just take f of 3 plus g of 3. Well, both of these are 0. Add them up and you get 0. And the same thing with scalar multiplication. So again, the idea of a set being a subspace means that whatever the defining property is for that set, it should be preserved under addition and scalar multiplication. And so the defining property for this example is that f of 3 has to equal 0. The value of the function when the input is 3 has to be 0. Is that preserved if you add them together or multiply them by a scalar? And the answer is yes. So it's a subspace. The P2 is a subspace of P3. Remember, P2 is a vector space. It is the vector space of all polynomials of degree 2 or less. And P3 is the vector space of all polynomials of degree 3 or less. And so automatically, since I know that two things, P2 is contained in P3, any polynomial of degree 2 or less is also a polynomial of degree 3 or less. And P2 is a vector space, and so since it's a vector space, it must be a subspace. All right, here I have three functions. They're all defined on the open interval from negative pi over 2 to pi over 2. Then their span, remember span, is the set of all linear combinations of those three functions, is a subspace. And that's the same thing that we saw in Euclidean spaces. You took a set of vectors, their span was always a subspace. And that's true in general. If you have any set, finite or infinite, of vectors, and you form their span, the set, which is the span of those vectors, is a subspace. Now we have to be a little bit careful about that, because we have to be careful that we're including in our definition the any possible new definition for vector addition and scalar multiplication. So suppose I've got a subset, W is a subset of V, and we have a different vector addition in W than we do in V. Or maybe a different scalar multiplication in W than we do in V. Then even if W with its new scalar multiplication and new vector addition is a subspace, on its own, it may not be a subspace of V with the different vector addition and scalar multiplication. And our example would be that mind-blowing one where we had the vector space where the set of vectors were positive real numbers. The way we defined vector addition was to form the product of those two real numbers, and the way we defined scalar multiplication was through exponentiation. In that case, well, it's pretty clear that the positive real numbers is a subset of the whole real line, and we can also consider the real line as a vector space. We can consider it R1, a Euclidean space, with the usual addition and the usual multiplication, which is different from this very odd one. So that means that W, considered as a subspace or a vector space on its own, is not a subspace of the Euclidean space R1. Other important subspaces are function spaces. So, for example, the functions that are continuous on an interval, we write that as C of I. They are a subspace. They're a subspace of the functions which are defined on that interval. And again, you can't add your way out of it, because if you add two continuous functions, the sum is another continuous function. If you multiply a continuous function by a scalar, the result is another continuous function. So it is a subspace. We could also look at the set of functions with a continuous first derivative on an interval I. They form a subspace. And in fact, that's a subspace of the continuous functions. So if a function is differentiable, it has to be continuous. But that we know that that's not the case. You can have continuous functions which are not differentiable. You know, the absolute value function, for example, on -1 to 1 is not differentiable at x equals 0, even though it is continuous at x equals 0. And we can continue looking at functions which have continuous second derivatives. The more derivatives, the more continuous derivatives a function has, we say that it's a smoother function. So if you have continuous second derivatives, you must have continuous first derivatives. Otherwise, you can't take that second derivative. And of course, that means it must be a continuous function. So you just get this nested set or collection of subspaces depending upon how many continuous derivatives you have. And in fact, you could even look at the set of functions which have an infinite number or which are infinitely differentiable. We call that C infinity. So C infinity means that there's infinitely many continuous derivatives. Functions in C infinity would be sine and cosine, the polynomials. All of those have an infinite number of continuous derivatives. So if I have a subspace, then I should be able to find a basis for that subspace too. So again, we have the same two conditions. If we have a set of vectors, it would be a basis for that vector space or subspace if it is both linearly independent and it spans the space. So our trivial vector space, which only contains the zero vector, does not have a basis, because remember, if you have a set with only one vector and that vector is the zero vector, then it's not linearly independent. So here are some examples. The first powers of x, so 1x and x squared, that forms a basis for any polynomial in P2. Of course, because you can write any polynomial in P2 as P of x equals C naught plus C1x plus C2 x squared. Oops. Meant to say x squared. There we go. And so certainly any polynomial, anything in P2 is a linear combination of those three polynomials or three monomials. And we also know that they are linearly, or they form a linearly independent set because they have different degrees. So if I look at all the powers, or all the monomials, then that's going to be a basis for P, which is the vector space of all polynomials. And again, we know that it spans the space. Any polynomial can be written as a linear combination of powers of x. And we also know it's linearly independent because if you take any finite subset, you're going to have a number of powers of x, all of them having different degrees, different exponents, so that's going to be linearly independent. So let's look at a little bit more involved example. Here I have a set e to the power of 2x, e to the power of 3x, e to the power of 5x. So I have different coefficients on x, so we had a theorem that says that this set itself is linearly independent. So it would form a basis for the span of that set. But what we're interested in is a different set, set S, which has 3 functions in it. E to the power of 2x, 2e to the 2x plus 6e to the 3x, and then negative 2e to the 5x minus 4e to the 3x. And so the question is, how can we show that this set S forms a basis for V? Well, what do we need to show? We need to show that S spans V, so any function in V, any function in the span of those 3 exponential functions, can be written as a linear combination of the functions in S. And we need to show that that set S is linearly independent. Well, let's start off with showing that S spans V. So any function in V should also belong to the span of S. We should be able to write it as a linear combination of those 3 functions in S. So let's just take a function in V. We don't know what the function is, but we know that it is a linear combination of those 3 functions in V. In the given set. That's what span means. And now if it's also in the span of our set S, then we have 3 other real numbers, and I'm going to use Greek letters, alpha, beta, and gamma. And we're going to say that, my function f must be a linear combination of those 3 functions in S with coefficients alpha, beta, and gamma. So I should be able to set those equal to each other, the linear combination of exponentials from the original set and the linear combination from the other set. Now what I've done is I've collected the like terms. So let me just go back here. I said that what is multiplied by e to the 2x? I have an alpha times e to the x. I have 2 beta times e to the 2x. What's multiplied times e to the 3x? Well, I have 6 beta and minus 4 gamma. That's multiplied by e to the 3x. And then the only thing that's left over is the negative 2 gamma times e to the 5x. So that's how we've written that. And now I can compare coefficients on each function. So if these two are equal to each other as functions, then the corresponding coefficients have to be equal to each other. So I wind up with a linear system that alpha plus 2 beta has to equal C1. Those are the coefficients on e to the 2x. 6 beta minus 4 gamma is C2. The coefficients from e to the 3x. And finally, minus 2 gamma has to equal C3. So my unknowns here, if you want to think of it that way, are alpha, beta, and gamma. C1 and C2 and C3, we can consider those as fixed because they define the function f. And so we could rewrite that system in matrix form. And hopefully you watched the video on structured matrices, because then you'll know that this coefficient matrix is what we call an upper triangular matrix. Even if you don't remember the nomenclature, you can easily tell that this matrix is invertible because there are no free columns This is not quite in row echelon form, but it'd be very easy to transform it to row echelon form, and from there you would see there's no free columns. So it must have full rank, and so it must be invertible. And since it's invertible, one of our conditions for invertibility is that if you have a linear system with an invertible coefficient matrix, it is consistent for all right-hand sides. That means it doesn't matter what C1, C2, and C3 are. I will always be able to find an alpha, beta, and gamma in order to make our system of equations consistent. And that's enough to show that we can represent any vector in V as a linear combination of functions in our set S. Now it also shows that S is linearly independent. Why is that? Well, because if I were to have a dependence equation, I would have the same situation, but instead I would have my right-hand side being all zeros. And since we know that we have an invertible matrix, then we know that the only solution then would be the trivial solution, where all alpha, beta, and gamma are 0. Now, it is possible to have infinitely many vectors in a basis for a vector space. But there can only be a finite number of vectors in a linear combination. So we would expect that if B is a basis for a vector space, we would be able to express V as a linear combination of vectors from that set B. And indeed we can. If we have a set of vectors and that set forms a basis, that's true if and only if every vector in V can be represented uniquely as a linear combination of a finite subset of vectors in S. So even if the basis has an infinite number of vectors, every vector can be represented by a finite linear combination, or a linear combination of a finite subset of those vectors. Now, does every subspace in general, so we know it's true for Euclidean vector spaces, but for general real vector spaces, does every subspace have a basis? Well, with Euclidean space, we had this extension theorem that said that if we had a set which was finite and linearly independent, and we were able to find another vector which did not belong to the span of S, then the augmented set or extended set is still linearly independent. It gets a little bit complicated, a little bit beyond the scope of this course to talk about what happens with infinite sets, but we're just going to accept it as a fact that every non-zero vector space has a basis B. So, for example, all the powers of x form a basis for the space of all polynomials, that is vector space P. And since there are bases with an infinite number of vectors, we have to be a little bit more careful how we define dimension. If we have a basis which only has a finite number of vectors, we call it a finite dimensional vector space. Otherwise, it's an infinite dimensional vector space. And again, as we did with Euclidean spaces, the trivial vector space is going to have dimension 0, and we consider it finite dimensional. And so in Euclidean space, what was the dimension? It was the number of vectors in the basis. And for finite dimensional vectors, that's the same thing. But in order to say that, we have to know for sure that every basis has the same number of vectors. And the tool that we used in Euclidean space is available in for general real vector spaces, which is our dependent or independent sets from spanning sets theorem. Essentially, it says that if you take a finite subset of vectors and look at the span of those vectors, then we choose a certain number of vectors from the span of our original set. What can we say? Well, if we chose more vectors than we had in the original set, the new set has to be linearly independent. Essentially, the number of vectors in the original set is the maximum number of independent directions that we could get. And so if I choose more than that, then one of them is, at least one of them has to be a linear combination of the other, so it would be linearly dependent. On the other hand, if I know that my new set is linearly independent, then I could not have taken more than the number of vectors that I started with. And from this theorem, we can conclude that any two bases for a finite dimensional vector space have exactly the same number of elements. And that number of elements is what we're called the dimension of the vector space. And if the dimension of the vector space is k, then we say that vector space is k-dimensional. Now, if we have infinite dimensional vector spaces, we have the same notion, but we replace the idea of number of vectors with the cardinality. So let's look at some examples. First of all, if we look at the first n plus 1 powers of x, so 1 up to x to the power of n, that's a basis for Pn, which means that the dimension of Pn is n plus 1. N plus 1. So there's, even though we still use this same type of notation, there's a huge difference between Rn and Pn. Let's just look at P3 versus R3. For R3, the vector space R2 is not a subspace of R3. R2 is not even a subset of R3. They're different objects. The objects that are in R2 are ordered pairs. The objects in R3 are ordered triples. So they're not even the same object. But with the polynomial spaces, the polynomials in degree in P3 are polynomials of degree 3 or less, which means that any polynomial in P2 is also in P3. So we were able to say that P2 is not only a subset of P3, P2 is a subspace of P3. The second big difference is that R3 is three-dimensional. P3 is four-dimensional. P2 is three-dimensional. P1 is two-dimensional. So it's just a difference that we just need to make careful note of. If I look at the set of all monomials, then we know that's a basis for our set P, which is a set of all possible polynomials. That's a countable set, so its dimension is the cardinality aleph null. And then if we looked at the uncountable set, which consists of e to the power of kx, where k is any real number, then its cardinality, which would be the dimension of the set, is aleph 1. All right, and then so the final result is that if you have any subspace of a k-dimensional vector space, then the dimension of the subspace is never going to be greater than the dimension of the vector space. So if the parent vector space is n-dimensional, then the dimension of V cannot be larger than n. And in fact, the dimension of the subspace equals the dimension of the vector space if and only if the subspace is the entire vector space.